Ever wondered what actually happens behind the scenes when you tap request ride on Uber? 50,000 ride requests in 1 second. Here is the hidden tech stack that makes it possible. Chapter 1: The 5 p.m. Disaster. It is 5 p.m. on a stormy Friday evening in New York City. Rain is pouring down. Subways are delayed. And over 50,000 people pull out their phones at the exact same second. They tap one single button. Request ride. At the exact same moment, 20,000 drivers are navigating treacherous city streets. Their phones pinging the cloud with precise GPS coordinates every 4 seconds. To a regular software developer, this sounds like a total nightmare. Hundreds of thousands of persistent TCP connections, continuous write streams, and complex spatial calculations, hitting your infrastructure all at once. If your system takes just 2 seconds to respond, the user cancels. If your database locks for 5 seconds, your platform crashes. Yet, behind that clean, minimal Uber interface, an invisible miracle of distributed engineering occurs in less than 100 milliseconds. Today, we are diving deep into the art of hyper-scale system architecture. This is the story of how Uber built one of the most advanced, self-healing, global load balancing networks on Earth. Chapter 2: The Illusion of Traditional Architecture. When junior engineers think about load balancing, they usually picture a simple setup. A user sends a request. An Nginx proxy receives it and forwards it to one of 3 application servers using round-robin. That model works beautifully if you are building an e-commerce store or a news blog. Why? Because web browsing is stateless. It does not matter whether server A or server B fetches your product list from the database. But ride-hailing is completely different. It is deeply stateful, highly dynamic, and tethered to the physical world. Imagine storing driver locations in a relational database like PostgreSQL. With 20,000 drivers sending GPS updates every 4 seconds, your database is forced to execute 5,000 spatial disk writes every single second. The write lock contention alone would bring the entire cluster to its knees. Now add the matching algorithm. To find a driver for a passenger in Times Square, you must query all nearby driver coordinates. If driver data is scattered randomly across different server memories, every request forces servers to query every other server in the data center. This creates the infamous N+1 network cascade. Latency spikes exponentially, hardware costs explode, and the system fails. Uber realized very early on, off-the-shelf tools would never save them. They needed a brand new architecture. Chapter 3: The 3-tier architectural masterpiece. To conquer this challenge, Uber engineers designed a brilliant 3-tier pipeline. Each tier has one job, and does it with absolute mathematical perfection. Tier 1 is the edge defense, built for raw hardware speed and packet distribution at layer 4. Tier 2 is the application gateway, powered by Envoy proxy at layer 7, responsible for intelligent microservice orchestration. And Tier 3 is the crown jewel, Ringpop, an in-memory application level routing cluster that solves spatial data distribution without touching a disk. Let us unpack how these three layers work together to conquer global scale. Chapter 4 Tier 1 The speed of Layer 4. At the edge of Uber network. Speed is everything. When your phone connects, it hits an edge point of presence. Here, Uber employs Layer 4 load balancers powered by Linux IP virtual server and hardware switches. Why Layer 4? Because Layer 4 operates strictly at the transport protocol layer. It looks only at source IP, destination IP, and TCP ports. It does not care about HTTP paths, cookies, or JSON request bodies. It does not even decrypt TLS encryption. By skipping heavy CPU operations, a single Layer 4 edge node can process millions of incoming network packets per second with near zero latency. It acts as a massive, lightning-fast traffic distributor, absorbing raw internet noise and fanning requests out across the Tier 2 gateway fleet. Chapter 5 Tier 2 Intelligent Orchestration with Envoy. Once traffic clears Tier 1, it enters Tier 2 Envoy proxies operating at Layer 7. Now, the system reads the actual HTTP application context. Envoy inspects path routes, parses headers, and validates authentication tokens. If the request is for updating credit card info, Envoy routes it to the isolated payment service. If it is a trip request, it routes to the dispatch engine. But Envoy does far more than just route URLs. It is the resilience shield of Uber architecture. It enforces circuit breaking, dynamic rate limiting, and automatic retry budgets. If the payment service experiences a temporary micro spike in latency, Envoy trips a circuit breaker instantly. Instead of allowing failing requests to pile up and crash downstream servers, Envoy sheds load immediately, keeping the rest of the application healthy and responsive. Chapter 6 The Geometry of Earth H3 Indexing. Layer 7 routing handles microservices, but it still leaves one massive question unanswered. How do you map a moving passenger and a moving driver in physical space to the exact same server instance? Standard GPS coordinates give you floating point numbers for latitude and longitude. You cannot efficiently load balance infinite floating point numbers across a fixed server cluster. To solve this, Uber invented H3, an open-source hexagonal spatial index. H3 projects the entire surface of planet Earth into a mathematical grid of hexagons. Why hexagons instead of squares or triangles? Square grids have a fatal flaw. The distance from the center of a square to its edge is different from the distance to its corner. Hexagons are pure spatial perfection. Every neighboring hexagon center is at the exact same distance. This simple geometric property drastically simplifies spatial radius calculations. H3 divides the planet into 16 resolution levels. At resolution level 8, a city is partitioned into hexagons roughly 700 meters wide. Every coordinate on Earth converts instantly into a unique 64-bit integer cell ID. Chapter 7 Ring Pop The in-memory ring of power. Now that physical location is represented by a 64-bit integer, Uber needed a way to route those cell IDs to servers without hitting a centralized database. They built RingPop, a decentralized application-level routing engine. RingPop runs directly inside the worker node code. It links all application instances into a unified, distributed hash ring using consistent hashing. Here is where the magic happens. When driver location updates stream in, RingPop hashes the H3 cell ID. The hash ring determines the exact server instance that owns that geographic cell. Both the passenger request in Manhattan and the 100 drivers surrounding them route to the exact same server memory space. The spatial matching calculation executes directly in RAM in microsecond speeds. 0 database disk reads. 0 cross data center fanout. Just pure high-speed in-memory computation. Chapter 8: Decentralized Survival. The Gossip Protocol. In a massive distributed cloud, hardware failure is not an anomaly. It is a daily guarantee. Servers crash, memory corrupts, and network switches fail. How does RingPop maintain its hash ring when servers die without relying on a centralized coordinator like Zookeeper? Centralized master nodes create fatal bottlenecks and single points of failure. Instead, RingPop uses the SWIM gossip protocol. Think of it like a human whisper network. Every server in the cluster continuously picks a random peer and sends a tiny ping. If server A does not hear back from server B, it does not panic. It asks 2 other servers to ping server B indirectly. If they fail to, server B is declared dead. This health update whispers across thousands of nodes in seconds. The distributed hash ring automatically rebalances itself. Surviving servers claim ownership of the dead server geographic cells, and traffic flows uninterrupted. No human intervention. No master node. Just pure decentralized self-healing resilience. Chapter 9: Dynamic Weights and Multi-Region Failover. Even with self-healing rings, real-world infrastructure brings unexpected surprises. Data centers contain heterogeneous hardware. Brand new servers run alongside older hardware generations. Sending equal traffic to unequal hardware causes older servers to overheat and choke. Overload balancers continuously collect real-time telemetry, monitoring CPU usage, garbage collection pauses, and RPC latency. The system dynamically adjusts routing weights in real time, pushing more traffic to high-capacity nodes while bleeding load away from struggling instances. Furthermore, Uber operates in an active multi-region cloud deployment. Primary worker nodes and hot standbys reside in isolated cloud availability zones. If a power grid failure wipes out an entire data center region, global DNS automatically redirects traffic to a backup data center thousands of miles away. The user on the street never notices a single glitch. Chapter 10: The Craftsmanship of System Design. What can we as software engineers learn from Uber load balancing architecture? First, decouple your network pipeline. Let layer 4 handle raw TCP throughput. while Layer 7 manages complex application business logic. Second, master data representation. Turning continuous, unindexable GPS coordinates into discrete, H3 hexagonal cell IDs transformed a mathematical nightmare into a clean distributed hash problem. Third, design for failure from day one. By leveraging in-memory consistent hashing and decentralized gossip protocols, Uber created a system that prospers in chaos. True engineering excellence is not about avoiding problems. It is about building systems that self-heal when catastrophe strikes. If you love deep dive software architecture stories like this, hit the subscribe button, like this video, and leave a comment below telling us which distributed system we should decode next. Thank you for watching, and keep building.